All right, this video will begin to look at Chapter 10 from our book, which is on confidence intervals. It's our first look at statistical inference, and that will be kind of the topic that we'll be spending most of the rest of our time, statistics time, or at least up until the AP exam on. So this is a fairly big topic. I think it's about 40% of the AP exam, so fairly important topic as we move forward. So let's first of all look at what statistical inference is. When we say statistical inference, we're basically saying, hey, we have a sample and we get data from our sample. Samples are fairly easy to get and get data from. But what we want to be able to do is we want to be able to take that sample and draw conclusions about the population, or in other words, infer from the sample data about the actual population. Okay? In Chapter 10, what we're going to do is we're going to look at the idea of confidence intervals. And in Chapter 11, we're going to look at something called significance testing. So those two topics are two of the most common types of formal statistical inference, and we will spend some time on it over the next few weeks here. When we use a statistical inference, you are acting as if the data are a random sample or come from a randomized experiment. So as we kind of go through this, keep in mind that we are making some assumptions about the data coming from a place where it's good data. If it's bad data, our inferences that we're going to draw are going to be bad inferences. So let's take a look at this example problem. This example was given to you in the book. If you want to pause the video and read it, that's fine. I'm not going to read through the thing, but here's what I want to focus on, and that is the actual question, which is, what can the director say about the mean score mu of the population of all 5,000 freshmen? So we're looking at 5,000 freshmen. We're looking at their mean of a sample as being 112. How can we use that to help and find the mean of the entire population? So here's what we're going to do. We have if we think about samples, well, how would the sample mean vary if we took many samples of 50 freshmen? Well, we know that each of those samples is going to be different, but we also know, based on Chapter 9 and the central limit theorem, that even if it's not normal, that it will approach normality if we have a sample size of 30 or greater. So we're going to, since our sample size is greater than 30, we're in good shape with that, so we can say that the mu of the x bars, in other words, the mean of the x bars of our sampling distribution, is going to be the same as the mean of the population. And therefore, the standard deviation of the sample distribution would be equal to the standard deviation of the population divided by the square root of n. Okay? So they didn't give us any information about the standard deviation of the population. So we're going to make some assumptions about that. We are going to assume that the standard deviation of the population is equal to 15. Okay, so that's not something you would have to figure out. That's something that would be given to you. So if that's 15, well, then we can find the standard deviation of the sample distribution, which would be 2.1. 15 divided by the square root of n, which is 50. Okay? So now we have a normal distribution that we're working with a standard deviation of 2.1 and a mean of 112. So really, here's what we're kind of working with. We've decided that we have a normal curve based on the central limit theorem. We know that the standard deviation of that normal curve is about 2.1. We don't know what our mean of the population is. That's what we're going to try and find. Now, we came up with a standard deviation, or excuse me, with a mean of our samples being 112, but each sample is going to be a little different. Okay, so it could be 109, it could be 114, it could be a lot of things, but probably are going to have numbers that are relatively close to that 112. So really, what this is a problem of inference. We will attempt to use x bar to estimate our parameter mu. So does this mean that mu is equal to 112? Well, no, probably. I mean, it could be something very close to that. It could be exactly that. It could be a little bit further away. But you know, it's a good place to start. Is kind of what the way that we're gonna work with this. We're gonna start with 112 and see if we can figure it out from there. So from an example standpoint, we'll start with x bar and mu as being x bar. And then what we do know is this, is that there's probably needs to be, in order for our estimate to work, we have to have some sort of error that would surround that. Okay? So we're basically thinking about it from the standpoint of we want to have a range of values. So from chapter 9, since we know then that mu of x bar is equal to 112 and the standard deviation of x bar is equal to 2.1. So we're going to work with that information. And let's just make the assumption that what we want to do is we want to say that we want to be 95% confident in our statement about the mean of the population. So when we're done, we want to be able to say with 95% confidence where mean would have to lie. Okay? So if we're moving from that standpoint, if that's where we're starting, what we're going to do is we're going to say, all right, well, we can use that 68, 95, 99.7 rule, and if we want to be within 90, have 95% confidence, well, we know from that rule that x bar has to be within 2 standard deviations of the mean of the population. Well, therefore, we can turn that around and just say, well, the mean of the population must be within 2 standard deviations of x bar. So we're basically just flipping around what we know from that rule. We're looking at the fact that if one happens, then it has to happen the other way as well. So what we're going to say is that the mean of the population is within x bar plus or minus 2 times sigma. So in terms of this particular question, we know that this value here is going to be 2.1, and we know that the mean is equal to 112, so I'm just going to use that to come up with my lower and upper bounds of a range of values where we're going to be able to say that mu is. So how do we write our answer for this? And now remember, I'm being very general on how we're coming up with this. We'll get a little bit more specific with that kind of as we move on with this particular section. But so the way that we would make our statement is we would say that I am 95% confident that the true mean IQ score is between 107.8 and 116.2. What we do not want to say is we do not want to say I have a 95% chance of the true mean being between those two numbers. Okay? The chance is already gone. Here's the way you want to think about that. So basically, if we think about our mean when we're talking about a confidence level, we're saying that mean falls somewhere in this in that green area. However, there's no chance involved. There is a mean, and it is somewhere in. We're just basically trying to say with confidence about where that might be. So what we've been doing here is we've been saying, okay, well, we can take a simple random sample, and with that simple random sample, I'm going to get a range of values. What we're saying when we say 95% confident, we're saying that of all of these simple random samples that I pull, 95% of them will have the mean within that, within their 4.2 on either side of it. Doesn't matter what simple random sample I pull, 95% of them will contain mu when I look at that range. So there's really only 2 things that can happen. And one is that the true value of mu will be within the range from 107.8 and 116.2. Or The other option would be it's one of the simple random samples in which the x bar is not within 4.2 points of the true mean, and therefore would not contain the true mean. This is only going to happen with 5% of the simple random samples that we pull. So here's our definition of confidence interval and confidence level. Okay. We say a level C confidence interval for a parameter has two parts. The first part is its confidence interval. Okay. And that's calculated from the data, usually in the form of an estimate plus or minus a margin of error. A confidence level C, which gives the probability that the interval will capture the true parameter of values in repeated samples. That is, the confidence level is the success rate for the method. So basically when we say we're 95% confident, we're saying we will be successful with 95% of our simple random samples. So here's kind of another way of thinking about this or illustrating this. If this is our normal curve, this is that unknown mean. What we've done is we've extended that down here as well. Now each one of these lines from arrow to arrow is kind of the range or our confidence interval for that particular mean, which is this dot here. So if this is another simple random sample, this dot right here is the mean, and this is the confidence interval. Now you'll notice that in all but one of these simple random samples, the mean is contained somewhere within the interval. However, this one right here, it is not within the interval. So if this were the particular simple random sample that we have, we actually would be one of those 5% values that is where the mu is not within the confidence range that we talked about. Okay? So that pretty much sums up the first part of 10.1. You should have your notes completed through this point, and we'll talk about the rest of 10.1 when you come to class next time.